Bom dia, pessoal. Bom dia. Sejam muito bem-vindos a mais um webinar aqui da VDI Brasil. Hoje nós vamos dar continuidade à nossa discussão sobre a indústria 4.0, né? De certa forma, aproveitando as curtas distâncias virtuais que nós temos atualmente, né? Com as restrições de viagens, e por isso temos hoje um convidado especial que vai se juntar a nós da Alemanha, um dos autores da nossa diretriz da VDI 4000 e também responsável por uma diretriz específica sobre o uso de Big Data na indústria. Então, um papo muito interessante aqui hoje, com certeza que vamos ter com Thomas Fröse aqui na sequência. Ele vai falar, né, como já indiquei o título, Aplicação de padrões alemães, né, os nossos manuais de boas práticas da VDI de Indústria 4.0 para reduzir efetivamente os custos de produção. Só rapidamente, para quem não conhece a VDI Brasil aqui entre vocês, né, a VDI na Alemanha, como maior plataforma de excelência em engenharia, foi a primeira instituição mundialmente a divulgar o termo Indústria 4.0 em 2011, e desde então, né, na Alemanha, com mais que 155 mil associados, 12 mil especialistas que participam na elaboração de diretrizes técnicas, né, de manuais de boas práticas. Então, esse trabalho também focou muito na questão da indústria 4.0 e aproximar os conceitos práticos do mercado. O nosso papel aqui como VDI Brasil, né, com uma estrutura menor, mas o nosso foco aqui é de trazer e adaptar esse conhecimento em indústria 4.0 para o mercado brasileiro e o intercâmbio de experiências e de conhecimento nessa área. Então, claro, esse webinar de hoje vai exatamente nessa linha. Como vocês viram, né, o nosso idioma de hoje vai ser o inglês. Então, vou mudar agora aqui, não só de apresentação, como também de idioma. So I would like to introduce right now to all of you Mr. Thomas Fröse, which is our special guest today, talking a little bit about two important standard projects that we have in VDI concerning Industry 4.0, and also about the practical implementation of these standards in the long run. So, Mr. Fröse, a warm welcome to you. Thank you very much for taking the time. And sorry, I have just to switch over to the other presentation. Just a second. Sorry for that. Just a short delay, but I think you can already introduce yourself while I open the presentation for everyone to see.
Yeah, good afternoon from Germany, or good morning to Brazil. I'm Thomas Fröse. I'm the chairman of Standardization Committee 7.24. You will see in a few minutes more information about that. And I'm a member of different other standardization committees. I'm very involved of the standardization of Industry 4.0. I think you have heard in the last weeks the presentation of Sebastian Schmitz from the Maturity Center of University of Aachen. He is one of a very close partner to our company, so we all work together on a better understanding of Industry 4.0 and the implementation of Industry 4.0. And I will show you at first what we are doing in our standardization committees to give you a general introduction into the technology and our type of thinking. It follows the explanations of Sebastian. Sebastian has told you about the measurement of the Industry 4.0 maturity. And we come very close to this. That means very often we do projects together in the industry. Mostly the colleagues from Aachen start with the projects and they measure the maturity of Industry 4.0, and then we are the second company and we implement Industry 4.0. How I can control?
Yes, just
okay.
Switch. Yeah.
Okay, it's a little bit slow. So I will start very simple. The first question, and I think that's a most interesting question: why big data analytics, or why Industry 4.0? That's the same. You can say you cannot do big data analytics if you have not implemented on a good way the Industry 4.0 maturity. And it makes no sense to implement Industry 4.0 maturity if you don't use big data analytics. So the both things come together. I will show you two core beliefs we follow in our company. The first core belief is think profit per hour. Very simple. If you have a production plant and you produce anything, a product, in general, you are not interested to produce a product, you are interested to produce money. It's very simple. That means you try to buy for a low budget energy, raw material, equipment, whatever, and people, and you make your product and try to sell the product for a very high price. That's a sense, that's the aim, that's the idea behind any production. That means if you make an analysis of your production process, the only interesting thing is, or the only interesting question is, how many profit you can produce per hour. What you can do to calculate the situation in your plant is very simple. Put the process data in 5-minute intervals into a table, add all cost factors for energy, raw material, equipment, and people to that table. And then you can calculate, and the price of your end product is very important too. And then you can calculate the profit per hour in 5-minute intervals. What you will see every time is that you have a high fluctuation. And if you think about what is the reason for the high fluctuation of your profit, then you can use big data analytics, and then you can learn what is a relationship between your manipulable variables you have in your process and your profit. And if you have a deep understanding of that relationship, you can make a function, and this function can describe the relationship between your actions, your manipulation of manipulable variables, and your profit. Then you can learn how you can make more profit. That's very simple. That's a basic idea. The second idea is think limits. That means you can calculate the theoretical limit of your profit at the end of your profit, and then you have an idea how good your production is. That means if you have for example, chemical production plant, and you can make $100 per hour with one machine or one reactor, and you have only 80, you have 20% potential between your profit you get and the profit you can get with your plant. And that's very simple. That are very good and clever ideas to start a project like this, because with this concept you can calculate on a very easy way what is your win you can get if you implement Industry 4.0. The reason for the fluctuation is very simple. At normally a production, you have 3 parameters. One parameter is a quality, one parameter is a productivity, and one is a cost. For the quality, normally you have a specification limit, and you are interested to come very close to the specification limit. The reason is you are not interested to sell a higher quality, then you must produce. That means if you have more control about your process, your fluctuation will go lower, then you can go more close to the specification limit. And that's a way to save money. That's very simple. And then you can go along this line of specification limit, and you have two possibilities. You can increase the productivity by reducing the cost, or you can decrease the cost by increasing the productivity. But to get this high level of control, you need a deep understanding of the relationships in your process. And that's the reason to use big data analytics, because only on this way you are able to understand how you have to influence or how you have to change manipulable variables to increase your profit. That's a basic idea. That means if you have successful project, then you can reduce your costs and increase your revenue, and then at the end you make a higher profit. One way to do this is you can put your historical data of your plant. That means all pressures, temperatures, levels, flows, analyzer signals, laboratory values, you can put into a table with historical data. And if you have this table of historical data, you can make advanced analytics or big data analytics. We have a tool that's called NeuroModel, and then you get at the end a model where you have a relationship, a function between your physical variables, and some of these physical variables you can change, you can manipulate, and the output of the model is your profit per ton, per hour, whatever. And that's a basic idea. And if you have a model like this, you can use this model together with an optimizer. And then you can say, okay, I have a model or many models. You have one or many KPIs, and this model you can use to say how I can manipulate these variables in a way that I have my given target quality with a lowest cost. And that what you here can see, that's a very generic scheme. That means at the end you have a precise model. And this precise model can generate a prediction of quality, of yields, of whatever you are interested in. You get the actual data from the process, and then the optimizer will calculate the best values for manipulable variables. And then you can generate proposed optimized set points to the process. And that means in every minute, your production will be in an optimal state, and you can maximize your profit. Okay, how we can do that? My answer is very simple. Follow the VDI 3714. The VDI 3714 is a standard I would like to present to you. And that's a standard what we have developed in our standardization committee. We have two initiatives. One is the standardization committee 727 and the standardization committee 724. That's Richtlinienausschuss. That's German for standardization committee. One is STEPS. You have heard about STEPS from Sebastian Schmitz. The chair is Dr. Violette Zeller, and the aim is a objective measurement of the maturity of Industry 4.0. I have told you something about that activities before, and you have heard it from Sebastian. And the second is my working group or standardization committee. This committee is called Big Data in Production, and we have developed the VDI 3714. The name of the standard is Implementation and Operation of Big Data Applications in the Manufacturing Industry with the target, optimize your profit. I'm the chairman of this committee, and the aim is to standardize the use of big data methods. And our understanding is that we have a work that will detail the execution of concepts of VDI 4000. Here you can see we have 30 active members. Some companies, Siemens, BASF, Clariant, Wacker, SKZ, IBM, Fraunhofer, some of the companies you will know. And you can say, I'm absolutely sure the 30 active members are the best people in Germany who are active in the field of big data analytics and big data operations. And we have in 2016 published some position or white papers. They are available under Big Data section of VDI.de. If you are interested, it's no problem. Please write me a mail or contact me via LinkedIn. I have published these papers in LinkedIn 2 weeks ago, I think 2 or 3 weeks ago. So if you contact me in LinkedIn, you can grab these papers, and these papers are very interesting because that's a type of draft of the VDI 3714. That means if you are interested in the content of the standard, you can grab these papers from LinkedIn, from my account, and then you have a very clear picture what we are doing there. The sheets 1 and 2 are finished. The sheet 3 follows in the middle of June. And we think we have finished all the sheets in the end of September. A sheet is not a sheet of paper. A sheet means it's you can say a chapter of the standard. That means we have 7 chapters, and 1 and 2 are finished. Now they are white. That means they are valid. 3 follows in June, and the other one by one in the next weeks. The final release of this standard we will expect at the end of this year. That's what you know. That's from the Maturity Center of Aachen. Sebastian has presented that a few months ago. That's the reason I say what we are doing is we describe in our standard how you can do that. The visibility and transparency you can do with the database, that's very simple. But to make a prediction of quality, yield, whatever, and to make your process adaptive, that means he will adjust itself to the best working point. That needs this algorithm, what we have described in the VDI 3714. Here you can see the structure. Sheet 1 is a part implementation of big data projects. It's like a cooking recipe, what you have to do step by step to come through a project with success. Sheet 2 is data quality. What's the definition of quality and how you can measure data quality? Because it's very simple. If you would like to design a model data-driven, also with the data, you need a very high quality of data. And the next sheet is data management, the ETL, extract, transform, load. That means how you have to extract and transform the data to make it available for big data analytics. Then in sheet 4, we have described analysis procedure classes. That means we have described methods. And what you can see, what's very interesting, here you can find only methods where we have practical experiences, but that are a lot of different algorithms. And at the end, here the implementation, we have only 1 or 2 algorithms what are allowed, because you have a very high level or increase of safety between 4 and 7, because in step 4 or sheet 4, you only try to analyze data, you try to understand relationships, you try to work with the data. And in sheet 7, you have to implement. And implementation means you have a lot of questions of safety, for example. If you would like to use an algorithm of big data in a methanol plant or ammonia plant or whatever, or in a refinery, it's very clear that we speak about safety aspects. And with the safety aspects, that means the funnel will be very close. So that means you have not so much possibilities. What you have here, or it's in sheet 4, you have a lot of possibilities. In sheet 7, only a few, because you have to be very safe what you are doing. Sheet 5 speaks about models. What are model types? Black box model, white box model, gray box model. It's only information about what is possible and what are the advantages and disadvantages of different types of modeling. I know a lot of people from the industry prefer white box models, the physical models, or first principle based models. And the advantage is, if you have a white box model, you have a very high degree of clearness about the relationships, and you understand the physical background of what you are doing. But you know, a lot of processes you cannot describe as a white box model, and then you have to use black box models. And that are definitions and discussions we have concluded to this sheet 5. Sheet 6 is validation of models. I think at the end you will get a copy of this document, and you can read that and you can understand it, because in reason of the time is running. I will jump over some detailed explanations of all the sheets and the contents, but you can read that later. Very interesting is a comparison of the process models. You can see here some process models or operation models to do big data analytics you will find in the literature and in the web. If you are surfing and you are searching for process models, you will find KDD, Zemma, CRISP, Six Sigma, and new is VDI 3714. And you can see we are very close to the Six Sigma model, but what we have done, we have defined all the steps with a higher precision, because today in the time the people has defined the first Six Sigma projects, that was, I think, 1980. And the computing power was not so high as it is today. That means you can do much more today. So we say our standard has a higher resolution in all the between steps what are necessary, because we can do more with the computing power today. Yeah, you can say, I see the comment from Mr. Rosa. You can say the VDI 3714 is the next generation of Six Sigma, but some of the Six Sigma things and procedures you can use today as you have it used in the past. That means we have done more than Six Sigma has defined. But you can use all the process models. That's very important to know. You can use all these models. That's allowed after this standard. And we give you the free choice what you would like to prefer. But I think our standard has the highest resolution. Yeah. Some general information from this standard is the most important point is, and that follows the Industry 4.0 maturity idea, you need complete data from the process chain. Like the CPOC standard in Six Sigma, supplier, input, process, output, customer. That means you have to understand from the state of the raw material over the machine process data. You have to implement full functional product tracking. You have to understand and to measure all the process states, and you need an exact, digital shadow of your process. Then you need open interfaces, such as OPC UA. That's a typical standard. All data must be available from one source. That Sebastian has told is single source of truth. That means you can use one database with all data from process control system or quality checks of the raw material. All this data has to be available over one point. You can put it in one database, that's one way. And the other way is you can make a few to different databases with different data sets. That's a very, very difficult thing. I know, for example, from Covestro, they have invested in the last year 50 million euro or US dollar, it's nearly the same, into a big database, and they had put all the data from different data pods or different databases into one database in Frankfurt. It was a really, really big project. Then, data with time response. If you have a high time behavior in continuous processes, for example, or you have a batch process, then you must do a pre-processing. This pre-processing, that is not easy. It is not easy to do. You need a deep understanding about your processes to do this. And then you can find with different big data methods correlations in the data. And this data-driven models are an ideal digital twin, we have learned. Yeah, and at the end, you have to develop a deep understanding of your model and of your process, and then you can implement a real-time optimizer, and this real-time optimizer can improve the process with the help of these models. I jump over these sheets that are more detailed explanations about what I have told you before, that you can read later if you are interested in more details. I will stop here in sheet 7 because in sheet 7 we go to the point operation of models, and operation is the most interesting point because if you have a fully functional model, a validated model, you are sure the model is really precise and follows the behavior of your process. That means it's a digital twin. Then you can use the model as a soft sensor. At first, you can extract knowledge from this model. That's the first step. Then you can use this model as a soft sensor. There are different levels of approaching these models. Then you can use the model as a predictor. You can predict the behavior of the process in the future. And then you can use this predictor for model-based control, not regulation. It's a not so good translation, model-based control. Then you can implement a closed loop multivariable controller, or you can support the operator by his decisions, and at the end it's a highest level real-time optimization. That means you can use the model to build a real-time optimizer to your process. And exactly in this chain 1 to 7, you can implement this technology. That means you can start with extracting knowledge and you can end with a real-time optimizer. And that's very, very clever to do this in this direction, because if you do a project like this too fast, you will kill your optimizer. You will kill your operator, sorry. That means the operator will have a big problem if you switch on a real-time optimizer and you say to him, hey, let the real-time optimizer do your work. Then you get a lot of discussions and problems with the operator. It's much more clever to go step by step through this application, and at the end, after 1 or 2 years, you can activate the real-time optimizer. And that are some things we have described in the sheet 7, operation of models, and a lot of informations, how you have to use watchdogs, incremental set point control, a lot of different concepts to make it safe, how you can check the accuracy of the measurements and of the models, and how you can implement rule-based safety strategies. And that are some things we have discussed in this sheet 7. Here you can see on a very easy scheme how we work if we do a project and we follow this standard. What you need is very simple. You have to capture all the measurements from your plant, and that means all the measurements to one database. Then you have to capture all the probes from the laboratory, quality of raw material and your product. And then you have to bring all the data into a single source of truth. That means the optimal case will be that you put all the data of your site into one database. And if we have a situation like this, we are more than happy. And that's what we check with our readiness checks. The readiness check means that we make an interview with you and we ask you, what is the data situation at your site? And with this readiness check, you get a readiness level. And if the readiness level is lower than a defined limit, then we say, hey, please change this, and then we can start with the project. Then we have to find a definition together. We have to find a definition. A definition means we have to define what is the target function, what you are interested in. Would you like to save energy, reducing one raw material because it's very expensive, increase your yield, whatever you like? We have to define it and we have to bring it into a target function. And then we have to define constraints. That means we have to define, okay, this quality has to be higher than or lower than. And this constraints and target function is very often not easy to find, because normally you are not able to drive your plant in a way that you can work every time at the optimal working point. And for that, you need a clear definition. It's a long discussion. Then we can start our extract, transform, load, because the way you have to select to do this ETL and to structure and clean your data depends from the definition. That means you make from your data lake the single source of truth with the rules you have defined in the definition phase. You have to make smart data. You have to extract these data sets, what are interesting for analyzing and modeling. Then we put the data into our engine. We build a model. In our case, the modeling is fully automized. That means we don't need any data analyst or data specialist. That's not necessary. What we need is domain experts. They have to understand what are the input variables, the possible input variables, what are the output variables, and I have to structurize my model or my models. Then you have to validate your models. That means, for example, you can use the data from the last year to build a model, and then you can use the data from this year to validate the model, to show how accurate the prediction of the model is. If you have a validated model, you can analyze the model and optimize, and that means you ask to the model the question, what I can do now in this situation to increase my profit. Yeah, back to the profit. Here you can ask what I can do to increase my profit. And if you have done all these steps on your desk, then at the end, you can decide to implement step by step this scheme and operate. And at the end, you have a closed loop. And closed loop means if you have a new condition in your plant, you will generate new data sets, and all the steps will go every day automatically. That means your model will adapt automatically to the process. It will be better and better. It learns different situations. And then you have a closed loop and a fully automated production with the highest quality and the highest output and the highest profit, what is possible with this physical set or situation you have available. We as Atlantec, we have our own interpretation of this standard. That means we follow the standard, but we have some specific changes or additional features we have added to the standard. It's very simple why we can do that. We have the experience from more than 1,000 projects, industrial projects. So we have a very easy configurable transformation for batch and continuous plants. That means to configure a batch process, we need maybe 1 day and not weeks. Then we have a software what makes it not needed to use data analyst know-how, because we have an expert system and that will decide and select automatically the best model, what is available for that. The models are not open, not editable, and not manipulable, because you have a safety discussion. And with Food and Drug Administration, you know, a lot of discussions you have. If you try to use open source, then you have to redo all these safety procedures for each project. And if you use a closed and validated software, it is validated and you can use that. And the reason it's not editable and not manipulable, you can make a new model, but that's a new entity. You cannot edit or change something. The reason is very simple: safety. Because if we make as company a model for a customer, then we have to be safe that no one has done some changes to the model. If something happened, then we have to be sure that our model is our model with a given identity. And that are things you have to think about if you start a project like this, because at the end, you have a safety discussion. Non-reliable manipulations in data are not allowed without rules. That means if you change or manipulate or delete some data, you have to implement fixed given rules, and the rules are a part of the validation of this project. Then you have to generate automatical documentation, and the workflow has to be consistent from the desktop to the controller, because every step between is dangerous for manipulations, and you have to inhibit these manipulations. The reason is very simple: safety, safety, safety. You can imagine if you go with a technology like this to a big chemical or refinery plant, you have a safety problem that you have to solve. Yeah, and we are independent from the database. We have started with Oracle, and now at the moment we have a big project. We are nearly finished to transfer our software environment to Azure, Microsoft SQL Azure. Yeah, here you can see how we can work together. The first is a scoping study. That means we are sitting together, or now at the moment we have projects in Thailand. And in Thailand, we have the situation we cannot travel to them because Corona, you know the situation. And what we are doing is we have a team in Thailand and they are doing the work, and we support this team via Teams from here, from Germany, and that works perfect. So we can do together with a team in Brasilia a scoping study, a proof of concept, and if there are difficult operations between, they can transfer the data to us, we can work with the data, then we discuss the results. And at the end, the industrialization, we will see how it works. We try to do it remote too. But I think in this case, that will be necessary that our specialists will travel to Thailand or to Brazil if it is recommended. Yeah, here are two of the ETL, this structuration of process data, two examples only. One is in the case of batch processes. You know, you have a lot of measurements, time dependent for each batch, but only one quality analyze at the end. And we have a specific software that's called a landmark extractor, and this landmark extractor will generate from this millions of data sets very small fingerprints. I have not the time to describe what we are doing in detail, but the definition says all. The batch fingerprint is the smallest set of data to identify any batch with, without any ambiguously. That means each batch is one record, and we try to bring the record to the most compact format, and that you can use then to put it into the neural network to make the data analyze and learn what is the impact of changing some of the input variables. In case of continuous processes, you have a time behavior. Here you have the stirred reactor, for example, and you can see in the case of stirred reactor, you have a stirred reactor time behavior. And in that case, if you have analyzed at the end of the plant, you cannot say, okay, here in the heat exchanger is sample. You can say, okay, if I grab at 6 o'clock here a probe, it was at 5 minutes before 6 o'clock in this heat exchanger. And you can bring the temperature in a cause-right relationship to this quality variable. But in case of the stirred reactor, you have a average band. That means you have a decline from the signal. That's a logarithmic decline that you have to calculate within our database. What we are doing, we are waiting to the next laboratory analysis and bring them together to a so-called causally correct data set. That means cause and effect are in one database. We remove the time behavior by a database-driven retention time model. That looks very complex. The configuration is very easy. The mathematics behind is not very easy. But we have a module like this, so we can remove the time behavior of processes. Then you have data sets without any time behavior, and that you can put into the engine, in the data-driven engine, and make a neural net model, machine learning model. And this model you can use in a way I have described in the sheet 7, for example. Here you can see a very simple implementation on an extrusion machine. That's a predictor. That means if you change, for example, the torque of this machine, that will be an input signal to this model, and this model will predict a physical property of the polymer, what will leave the machine at the end. Here you can see implementation of our model from the bird perspective. Here you can see the blocks for OPC. That's how we can read the modules from the DCS. Here we have a check section. That means we will check the variables for quality. A simple example, if you have a temperature, and normally you have a small noise on the temperature. And if you see this temperature will not change over 15 minutes, that will be absolutely stable, you can be sure something is wrong. And then you have make an alarm and you have to stop the model calculation, because in that case, the accuracy of the temperature measurement is not high. And that is one of hundreds of tricks we have here. Here is the equalization section. Equalization is the reverse process of this here. Because if you follow the signal through the plant, you know, if you change, for example, the raw material, it will need 2 hours to come to the end of the plant, or 12 hours, or whatever. And that's a calculation section. We can calculate the time behavior of the plant. That's a model section. That's the optimizer section. And here you write the set points and the predictions back into the control system. And now I will show you a zoom to give you a feeling how it works. You see that are function blocks. You can bring them together. That here, for example, is a average value, average of the last 8 hours for here in this example. And here you have the soft sensors. That means that are the machine learning modules. Here we have, in this case, used a mass balance to check the quality of the variables. I know in the most chemical plants, the mass balance is not accurate. That's not a problem, but a problem is if it has a drastic change, then you know, okay, something is wrong. That means with this mass balance modules, and normally we check only the stability of the mostly wrong mass balance. And here you go to the machine learning, and then you have a decision, and the decision will go to the control system. That's a big example, and this example is interesting in one reason. We have a cooperation with Chem Stations. You know, Chem Stations is one of the companies, I think it's a number 2 worldwide. They build first principle based models, physical models. And in the last time we had some projects, we worked together with this ChemCat. And the interesting point is, for example, ChemCat is very good able to predict the behavior of distillation columns, for example. They have really very precise models, but they are not able, for example, to predict the behavior of some reactions, or if you have a gas phase reactor, for example, with a solist catalyst, they are not able to predict this behavior. And if you put both models together, you have an ideal combination between white box and black box models. And so you can build very, very complex systems. That's only a part of the system we have implemented on the customer side. To give you a picture, the biggest systems we have implemented have 38,000 function blocks. So you can see what is possible. And big data analytics is a very important part of these models and this solution. Okay, then at the end, I think we have 10 minutes. I will show you some successful applications we have done. Most of them are from the chemical industry, but we are able to do projects in pulp and paper industry, in textile industry, in plastic industry. So we have a lot of applications. You can imagine we have 1,000 successful industrial projects. So if you have a question to a specific area, you can ask me, you can contact me. I can show you some examples, or we can discuss your case in a separate conference. So I'm very open for that. The first application is in an ethylene oxide plant. Ethylene oxide is a very important basic chemical. But you know, ethylene oxide is poisonous, explosive, burnable. So you have a lot of different reasons to make an application like this very safe. And here, in this case, we have saved $20 million per year because we have brought the baseline from 95% to 98%. Here you can see the accuracy of the model. Now you have the question why the selectivity is a target function we have, will decline. That's very simple. That's a aging behavior of the catalyst that are days, 0 to 500 days. And you see the catalyst is a solid catalyst, has an aging behavior, and we can predict very precise the aging of the catalyst and the behavior of the plant. The black is a real measurement of the analyzers, and the yellow is a prediction of our model. Second example is from a company. They do a type of polymerization. You have two adducts and one catalyst. They put them together in a reactor, and then they have a heat exchanger to cool the reactor because it's an exotherm reaction. And the tricky thing is you have to cool in a way that the temperature will not be too high. Otherwise, you will get a color in the product. Or at the end, carbon. You are not interested to produce carbon if you would like to produce polymer. That means you have to cool in a way that you can control the reaction, but you are not interested to cool so hard that you stop the reaction. So it's a very fine adjustment you have to do. And we have two correction parameters. One is enthalpy, so we can measure the amount of heat we extract by the cooling heat exchanger here from the reactor. And we have a signal for the viscosity. We don't measure viscosity, we measure the power consumption of the engine. Because if you have a high viscosity in the reactor, you have a higher power consumption. It's very simple. So we can use the power consumption of the engine as a substitutional signal to estimate the viscosity. That's one of the advantages of big data analytics, because that's the way how you can work, because you can put every value into this data-driven model. The data-driven model has no idea about the physical background. The only thing you have to be safe is that there is an intelligent reason to estimate there is a relationship between the power consumption of the engine and your yield or the viscosity at the end. Then we have the same signal from the second reactor, and this model is very precise, able to predict the yield and the viscosity. And you can imagine what happened. If you have a very high yield, you have a lower viscosity. The viscosity is a quality value. That's an estimation of the degree of polymerization. And the yield is the amount of product you can produce with this plant. Then we have an optimizer, and this optimizer will have influence to the catalyst and the concentration of both raw materials. Yeah, at the end of the product, we had 5% savings. That sounds not many, but you know, a big chemical plant, they have thousands of tons per day. And so you can save, at the end, many $1 million per year with a scheme like this. Then we have implementation together with Huntsman. Huntsman, I think they are known in Brazil. Huntsman is a chemical company from United States. They have published this project we have done together, and you can see only the result of a project. We have here a separator for a water-based mixture and the organic mixture, and we have to separate that. The organic is a product that goes to a production of isocyanate. Isocyanate is a raw material of polyurethane. It's a polymer. And we have a wastewater treatment plant, and you are not interested to put too many organic substances to the wastewater treatment plant, because in that case, the microorganism in the treatment plant will die. Then you can stop your plant. And that's the reason the operator has driven the plant very carefully, and carefully means wasting energy. And we have implemented our system, and here you can see the effect. We have reduced the steam usage by 12%, and we have produced 11% more product. And that's a lot. It's a mess of money. They don't speak about the money, but they speak about the big success. And at the moment, we are doing some further projects together with Huntsman in Rotterdam. That's what we have done in a methanol plant in Near East. Here you can see the drive of the operators, and here you can see the drive of our optimizer. The unit is profit in dollar per hour. And that means we have saved to this customer 3 million per year. And if you calculate a project like this, needs, if you have a good situation in a plant, it needs 2 months, 3 months. The costs are between, that depends from the situation, 100 and 350,000 euro. And you save 3 million per year, and you can say you have a return on investment of 4 weeks, 5 weeks, something like this. So it will be a fool if he will not do a project like this, but you can't imagine how many companies in the world are fools like this. Yeah, and that are some projects we have done in the batch environment, batch polymerization plant, adhesive production, carboxylic acid fermentation. And you can see in all that cases, we have reduced or improved the yield, an average of 37 to 81. And that means you can produce 10% more per year at minimum. Yeah, and now I think I'm at the end. On time, I think 2.5 minutes before I have stopped. And if you have any question, yeah, please ask. Mr. Klingberg, I don't know how it works here in this forum. Maybe you will moderate. If there is something to explain, I can do so. Thank you very much.
Thank you very much, Thomas. This was really impressive. How you explain the benefits of implementing big data and analytics in a practical industrial context. If you have an additional 10 minutes, we could go into 3 quick questions, if you agree.
Yeah.
The first thing would be a question of my side. Currently the Maturity Center, the colleagues at the Maturity Center, they published the actualization of the maturity index, and they put out some results of their experience with the digital transformation of companies so far. And when you see the digital maturity level of those companies that they worked with, those that are considered in Industry 4.0 already are at best in a level of visualization, or they manage to get some kind of digital shadow and a single source of truth, etc. But you don't see companies that are yet getting into a level of really using analytics, which would be the next steps towards a higher degree of digital maturity. What do you think is really missing for companies to implement these tools and these methodologies that you just presented. Can you make any sense of why companies aren't doing it yet?
I think the main reason is the structure of the companies. That means if you have looked to the structure of the most companies, for example, if they have, as only one example, a white box department. If you look to big chemical companies, they have a white box department. And this white box department, white box modeling department, is fighting against big data analytics because they are losing their jobs. It's very simple. The same you have with the Six Sigma people. They have not recognized up to today that it is necessary to save their job for a long time perspective, that it is necessary to switch to this technology. That means, and that's what we see, if we go to companies with a middle size and they have not these departments, they are much more open for this technology than, for example, big chemical companies. If, for example, one in a big chemical company in Brazil is interested to introduce a technology I have showed to you, they will get a call from Ludwigshafen. I know the name, I don't say the name, and he will say, no, we don't need big data analytics, we have white box models. I think that's the main reason for this slow degree of evolution.
I see. Yeah, makes a lot of sense. Just a quick question from Tarcísio. Is asking about the integration to ERPs and to PLM with your data model, if your models are connected both to ERPs and PLM model softwares.
I think that's like a question about the utility. I think we have to be very open about the utilities. I know some paper companies, pulp and paper companies, they have used SAP as a utility to build a single source of truth. I have seen companies, they have used OZPy to make it. That means we have to be open about the utility, but the target is more important. That depends from the structure of the company at the moment. And then you have to think about or discuss about which tool you have to use and what's the cheapest way to get a single source of truth. Also in that, I'm absolutely open.
Okay, we have to keep that flexibility in this point. Okay. A last question here from Maria Helena, asking about 20 years ago, the plant where I worked used a PI system as PIMS, and almost decided to go for Pavilion as a model simulator. Petrobras refinery adopted that solution, so Petrobras is working with that software. What are the difference between PI and Pavilion and your project and your model that you use?
To say it in one word, 20 years.
Good.
20 years. That means it's like the difference between an old timer from 1910 and a BMW from 2010. We have implemented a lot of time, and not we as Atlantec, we as a standardization committee, and we as Atlantec, and we as RET Aachen. We have implemented a lot of man years and hours to make it much more better and to solve the problems what the older systems had and have up today. I know Pavilion very, very good. And we had bought some people from Pavilion. They have closed here in Europe, and I have paid them to explain us what they are doing and to make it better.
Mm-hmm. Okay. Great. I think that answers that very quickly as well. Just one last question, if you're okay with it, from Thiago at this point. How prepared are people in the companies you have worked in to apply and accept these concepts?
Yeah, the best way is education, education, education. Mm-hmm. That means you have to pay money, you have to implement procedures, you have to train the people in every department, and you have to work together with the people about these concepts. I think that's the best answer I can give.
Okay. Any particular skill set or something that you really missed in some of the projects when working with the staff of the company? Something particular that you can remember?
No.
Without saying names, of course.
No. I would say I don't miss anything. I think that makes sense to bring process experts or domain experts into these projects and train them, and not data analysts, because data analysts, they have no idea about the process and the production. And in my experience, data analysts are more blocking and inhibiting projects like this. And if you have process and chemical engineers and machine engineers, electrical engineers, you are much more better prepared for that. That's my experience.
Great. Thank you very much for your time. Thanks everyone for your engagement, for your interest in this topic. We will share the presentation and of course your contact, Thomas, with everybody that joined us today. So if there are any further questions or ideas for possible projects, they will get in touch with you.
One last remark, we are working on a concept that we will do together with the VDI trainings in this area. Mm-hmm. But I think that you can distribute if we have official confirmation of the VDI, you are able to distribute that in your environment.
Definitely. Yeah, we're looking forward to that. Thank you very much, Thomas.
Thank you for your time and have a nice day. Thank you. Bye-bye.
Same to you. Bye-bye.